Yes, my name is Jiri Novak. I'm from Czech Republic. I work at the Czech Technical University, and my lecture is about obstacles which prevent achieving very good air tightness in multifamily residential buildings. In the Czech Republic, we have a quite long experience with construction of airtight building and with airtightness testing. We started to construct the first passive houses around the year 2000. In 2009, Ministry of Environment launched a program of financial support for construction of passive houses. So since this time we have collected, I think, a good knowledge and a good experience in design and construction of airtight single family houses, because we started, of course, with small houses, with single family houses, and we are able to achieve good airtightness in practice, which is proved by measurements. On the other hand, we have only limited experience with airtightness of large buildings, for example, residential multifamily buildings, and now, due to some changes in legislation, in technical standards, we are facing the challenge to achieve a very good airtightness in multifamily residential buildings, not only in passive houses, but in standard production or standard construction as well. So a lot of building practitioners think that it should be quite easy because we have this know-how from single family houses, and because the large buildings have a favorable geometry. But the problem is a little bit more complex. This is a statistical analysis of airtightness test results performed in single-family passive houses. On the left-hand side, we can see the measured N50 values, and we can see that a large majority of the buildings can fulfill or fulfills the passive house requirement of 0.6 air changes per hour. So I think it proves that we are able to achieve a very good air tightness in building practice in Czech Republic. And on the right-hand side, we can see the same results expressed in terms of envelope air permeability, QE50, which is an indicator directly expressing the airtightness quality of the envelope, let's say. And we can see that the majority of the buildings, once more, can fulfill the value 0.6 cubic meters per square meter and per hour. This is the air leakage normalized to at 50 pascals, normalized to 1 square meter of building envelope. So 0.6 is something which is very good. It's a very good airtightness, and it seems that the Czech building industry can achieve such a good result if the principles of passive house design and careful construction is applied. So we can achieve these results in single family houses, and there is no reason that it could not be possible in multifamily residential buildings. Even more, we can expect theoretically even better N50 values because of the favorable geometry. Here we can see the relationship between the N50 and the exchange rate, and the QE50, the permeability of building envelope, and this is the so-called area to volume ratio. This is the envelope area, and this is the volume of the building. It can be demonstrated. I will not do it, but it can be done. That this ratio tends to decrease with the size of the building. It means that with the same QE50, we will obtain better N50 values for large buildings. This is an example. This is a single family house. The envelope to volume ratio typically for small single family houses is around 1. So with envelope air permeability 0.6, we will obtain the N50 equal to 0.6 as well, which is just right the limit for passive houses. So if we take this building, multifamily residential building, rather small, its envelope to volume ratio is 0.56, and with QE50 0.6 we will obtain much better N50 values, 0.3. And finally, this is our faculty building. It has the envelope to volume ratio only 0.18 because it's a large building. And if it would be, if it would have the QE50 0.6, we would obtain very nice N50 value of 0.11, which is very, very good air tightness. So theoretically, it seems that if we would be able to reach the QE50 value 0.6, we would obtain very low N50 values, even in case of multifamily residential buildings. But the reality is really different. This graph shows the measurement results of 21 multifamily residential buildings constructed and tested recently in Czech Republic, in Prague. So these figures at the bottom of columns indicate the area to volume ratio, and the gray columns indicate the expected or theoretically calculated N50 values under assumption that QE50 would be 0.6 cubic meters per hour and per square meter of building envelope. So this is a theoretical value. We can see that if the QE50 would be 0.6, which is achievable perfectly in single family houses, as we saw before. All these buildings could easily fulfill the passive house limit of N50 0.6. But the red columns indicate the real results, the measured results, and we can see that none of these buildings has the QE50 equal to 0.6. They have a larger, bigger open QE50, and many of these buildings don't fulfill the passive house limit. So this is something which is not in line with the theory and with the expectations, and we try to investigate the reasons behind. So first of all, let's have a look on these buildings studied. They have all a very similar layout. They have an underground parking, unheated underground parking, and residential part above the ground, consisting of heated residential units. And we have always a stairwell or staircase connecting both parts of building together. The stairwell is heated, so it should be airtight as well. These buildings are designed as passive houses. They feature balanced mechanical ventilation system with heat recovery, but the staircases are ventilated separately by means of either natural or mechanical ventilation system without heat recovery. And in the stairwells, there is a fire safety, smoke pressurization control installed with a fan at the bottom and smoke vents at the rooftop of the staircase. So, and they have, all these buildings have a massive structure, masonry or concrete walls, and concrete floor slabs. For the first step that we did was leakage detection, very simply by means of an anemometer with under pressure of -50 pascals inside the building. And this is the list. This is the list of the leakage paths that we found. We can see several sources of leakages, and here in this column we can see the number of occurrences of each leakage path in this group of buildings. So mostly three sources of leakage. First, the building elements like the doors to adjacent underground unheated spaces or roof access hatch. Second, some penetrations of building installations, like, for example, penetrations of large ventilation ducts from underground spaces to the heated space. And also building services, some ventilation equipments like ventilation openings or ventilation systems for the elevator shafts represent a very frequent source of air leakage. Yes. And here we can see the list of leakage paths that we found in the envelope of residential units. We can see that the frequency of this leakage path is much lower, except for case of penetrations of installations through the slab above the first the underground parking. So the penetrations from heated space from residential units to the unheated parking in the underground. So, and this is the list of both types of leakage paths combined together, and we can see that most frequently the leakage paths occur in common spaces. It means in the stairwell and adjacent corridors. So, and it's very interesting that this kind of leakage path is very specific for residential buildings and don't occur in single-family houses. So it seems that the designers and the builders of these buildings, they were able to recognize the standard problems from single-family houses. They were able to address them and resolve them, but it seems that they were not aware at all about specific problems that can occur in larger buildings, in in these residential buildings. So in the second step, we try to quantify the air leakage through selected leakage paths that we have found in the previous step. The leakage path from the common spaces. For this purpose, we used the so-called reductive sealing method. I will not explain it because of the time, but I think it's clear from the slide what's going about. And I would like just point out that this method is quite good, feasible, but it has a very large uncertainty for some reasons. So here we can see the results, and we see that the air leakage through this specific leakage path is very, very significant, several hundreds of cubic meters per hour, which can influence significantly the air tightness of the whole building. It has several thousands of cubic meters of internal volume. This graph shows the contribution of this specific leakage path in common areas in multi-family residential buildings to the overall air tightness of the building. And we can see this is really based on measurement. We first measured the buildings as they were with a standard building preparation, and then after sealing one or several leakage paths in the common spaces, and we can see very big difference. And even after sealing this leakage path, many of the buildings or some of these buildings were able to fulfill the very strict passive house limit value. So it proves that these specific leakage paths in common spaces are very, very significant in case of multifamily residential buildings. So to conclude, the first interesting point is that it seems that the problem is that we have a very specific leakage path in common spaces, which were not identified and addressed in the design phase. And all these leakage paths, in fact, could have been resolved in the design phase. So it points out the importance of very good design if we want to achieve very good air tightness. The second point is that obviously different building types have different air tightness issues and different leakage paths, very specific leakage paths. So we cannot simply take the experience from one kind of building and apply it to another and expect very good results. We have always to think about specific problems of each building type. And for this reason, I think that we need not only improve technical solutions for specific building elements or details, etc. This is not problem. I think bigger problem is that we need really good design methods and guidelines and tools allowing for identification of potential risks in the design phase, and the methods to develop a reliable and good air tightness concept. And of course, we have to introduce this information into the standard design documentation. So, thank you.